with what we did last week, except for I have to stand right here because of all the technology. I've got something that just doesn't work right on my tablet right now. So we've talked already about moment of inertia and the center of mass, and today I'm going to be focusing on moment of inertia. So when you're calculating the moment of inertia, what does it mean? You know, when I say moment of inertia, what does that mean? Okay, so rotation equivalent to mass. What do you say over here?
Propensity to stay in rotational motion.
Okay, propensity to stay in rotational motion. Those are both really quite perfect answers. They both describe exactly what we're talking about with rotational inertia. So as we go through this, let me point out that for your exam next week, you will have a calculus problem. And your calculus problem will either be finding the moment of inertia or the center of mass for some object. And it's going to require calculus. Now, how could it require calculus? It could have a constant density, or it could have a density that varies. So far, everything I've done was a constant density, I think. Did I do a rod with a varying density? Okay, so I will go and do a rod with a varying density right here, just so you have seen the process. So now, let's do this one, the moment of inertia for a rod with varying density. So I will just make a little contrived problem here of having a uniform rod that I'm going to rotate about that axis. That's supposed to be a vertical line. And so my rod is going to have some length, or not a uniform line, rod, some length L and a non-uniform density. Now, this rod, everything in reality has a volumetric density. That's a mass per unit volume, because everything in reality is three-dimensional. But to simplify our problems, we might say, okay, this rod is going to be uniform in cross-section. That means if I were to take a slice somewhere like right here and look at that slice, everything's the same on that slice. And in that case, I can simplify, and instead of saying my dm is equal to rho dv, I can say my dm is equal to rho times that cross-sectional area times dx. And the rho times cross-sectional area, I will just call lambda for the lineal mass density. And so I'll define lambda is equal to the mass over length is the lineal mass density. And in this case, I'll give lambda is equal to lambda 0 plus, let's use a and b instead. A plus b x. So now the density starts with density A and increases linearly as you move out. It's kind of contrived. When we get to the Earth, we'll see a different form that's more realistic, and we won't have a nice equation for it because realistic and equations aren't always exactly compatible. So given this lambda, if I want to find the moment of inertia, look back at the moment of inertia equation, I is equal to the integral of r perpendicular squared dm. What does r perpendicular mean?
Perpendicular distance from something.
Perpendicular distance from something. From the axis about which it would be rotating. So I said that I'm going to have it rotating about this axis. So r perpendicular is the distance from that axis out to, well, away from it. It doesn't matter if I go up or down because that's parallel to the axis. It only matters how much I move perpendicular to that axis. So our perpendicular is measured like this. Well, using my traditional XY coordinate system and setting the origin right there for x, then my R perpendicular is just equal to what variable? X, right. So I use my equation, I is equal to the integral of R perpendicular squared dm, and then do substitutions. For dm, I'm going to put lambda dx, and for R perpendicular, I'm going to put x. So I'll have x squared, that's R perpendicular squared, times lambda dx, and for my lambda, I have to substitute the equation above. Now there's one more thing missing before I can do the integral. What's that one more thing? Limits. So what are my limits for length if I put 0 right there at the end? 0 to L. Now I just do my integral, x cubed over 3a plus x to the 4th over 4b. Put in my limits 0 to L, and I have L cubed over 3a plus L to the 4th over 4b. Or if you preferred, I could factor out the L cubed and have it's the same thing, just a slightly shorter way of writing it. And by slightly, I mean really no difference. So there I calculate the moment of inertia about that axis I defined for this object. That wasn't overly difficult. The scores on the calculus problem on the last test ranged fairly significantly. I want to make sure people know you're going to have to do something like either center of mass like this. It may be a constant density or it may be a changing density, so you need to know how to deal with it, just like I did here. So any questions about this center of mass problem? Yes, Michael.
So as far as the lambda equaling a plus bx, is that just something that...
That's something that would be given to you.
Okay.
If it's not uniform, I would give you something to let you know what it is. Yes. Got another question?
Yeah. And then as far as dm equaling rho a dx,
Mm-hmm.
can you walk us through that process, how we would find that?
Okay, this here is a definition.
Right.
Okay, or to put it more succinctly, the density is dm over dv. That's the definition of density. And then I said, if I have a uniform cross-section, then I can put my density, or my dv is the area of that uniform cross-section times dx. Right, so I made a substitution for a uniform cross-section, dv is a dx. If I didn't have that, but I had something that had, well, you can have, I'll just write the three options in a different color over here. Blue is the same color. If you have a problem that can be broken down into one dimension, if it only has variation in one dimension, then you can have dv is equal to a dx. If it's two dimensions, if you have variation in two dimensions like x and y, then we put, well, L dx dy And if it's, of course, 3 dimensions of change, then you would have dx, dy, dz. And so in these cases, we put dm is equal to, in the top one, lambda dx, the middle one, sigma dx dy, or sigma dA, and the bottom one, rho dx dy dz, or rho dz. So we have those 3 different forms for rho, or for dm, depending on if I have a 1-dimensional problem, variation only in 1 dimension, 2-dimensional problem, variation in 2 dimensions, or a 3-dimensional problem. So if you have something like a, well, you can always use the 3-dimensional, but if you can break it down to 2-dimensional, 1-dimensional, make your integrals easier, you like to do that. So I could have taken something like this, and if I had wanted to, I could have said, okay, I have a rod, and actually, I guess I'd better put a blank page in between here. Come on. Okay. Put a blank page in between here so I can go to the blank page. And I could have said that I have, to make life easy, I'm going to make this a rod that is rectangular. Rectangular rod. And then I would have still rho is equal to A plus BX, all multiplied by capital A, because the uniformity, right? So I have my density now is going to be, oh, not multiplied by, divided by capital A. Mistake. So my density is the linear density divided by the area to get the volumetric density. So that's a conversion back to something that's volumetric using the same definition I had before. And now when I do my integral from minus width over 2 to width over 2 dy minus, oh, I don't even know what to call it, thickness over 2 to thickness over 2 dz. And then I have my 0 to L. My r perpendicular is still going to be x, so x squared. But then for dm, I would have rho dx, dy, dz, except for my y and z I already put. And then I put in this rho. Now, if you look at that integral, it has 2 additional integrals, right? But this is complete. This is treating it 3-dimensional because it really is 3-dimensional. But of course, this here is just going to give me the width. This here gives me the thickness. And so these multiplied together are the area, and that cancels with that area. So instead of doing these 2 trivial integrals, I said if it's uniform, I can take them out. Is that a reasonable thing? Looks like I have some buy-in, but not complete buy-in on the reasonableness of this.
Can you explain again how we got the lambda equals m over L? Is that just the definition thing?
Yes. If you define a problem as 1-dimensional, then your mass is only laid out over one dimension, right? And so that means your mass density would be the mass per unit length because it's only one dimensional. And so we use the symbol lambda for the mass density. So lambda would be defined as dm dx.
And we can do that when we have the cross sections are all the same, right?
Yes.
Okay.
If you have a, it's uniform in 2 dimensions and only changing in the third one. Now, if somebody wants to get really, really, really picky with me, you can get really picky. Because as soon as I introduce my dimensions for y and z here, then quite technically, the distance from the axis I'm integrating about is going to be square root of x squared plus y, or plus z squared or y squared, depending on which one is the perpendicular one. So if I call, well, I already did. I called the axis I'm rotating about the y-axis. And so if you wanted to be really picky, this would actually have been x squared plus z squared. And if z is changing by a reasonable amount, it does make a difference. So if you have a rod that is, like 2 inches by 2 inches by 6 inches, and you're rotating about the end of the rod, you're going to have a very slight deviation from the equation that's given in the textbook for the moment of inertia for a rod. Because you have, material that is at a distance 0 this direction from the rod, but it's still an inch this direction away from the rod. So it still has a moment of inertia. Even though it's at x equals 0, it has a moment of inertia because it's not at the rod. So that is a pickiness that makes a difference if you have a rod that's short compared to its thickness. If it's long compared to its thickness, then it's negligibly small. So for things like the table shown in the textbook, there's a caveat for a rod. They show circular rods. So it's for a rod that is long compared to its radius. Okay, I am going to move forward now. I skipped over this calculation last class period for time. I added a few details here for the slide. That is the cylindrical coordinate information. If you have a flat disk, it's usually more convenient to use coordinates that match the geometry. So this being cylindrical, we use cylindrical coordinates. The cylindrical coordinates have an angle in the xy plane, the xy plane being defined as the plane that is normal to the symmetry axis of the cylinder. Z-axis is the symmetry axis of the cylinder. And so you see the z-axis stays as is, but you have an angle in that plane normal to the symmetry axis, and then the distance from the center is r. So you have 3 coordinates, the radius, the distance from the center going outward. You have the angle from your reference of the x-axis, and then you have the height, z, that it is from the base, or from the origin. So those are your cylindrical coordinates. Depending on what textbook and what discipline you're in, you might see theta used for this angle, or you might see a phi used for that angle. You'll have variations. I personally prefer to use a phi because when you go to spherical coordinates, we use theta for the angle from the z-axis and phi for this angle. And so I like to use phi so it's the same for both cylindrical coordinates and for spherical coordinates. At any rate. It's just a name. As long as you keep it straight in your head, It won't be a problem. When you're using a different set of coordinates, of course, you're not going to have dv equals dx, dy, dz if you don't have x, y, and z as your coordinates. So you have to convert to the new coordinate system to find what dv is. So here is drawn a portion of dv. This is something that is like out here, and you have some d theta, and you have some dz, and you have a dr that comes out this direction. Except for one thing. The length of the arc is not d theta. What's the arc length? If the arc goes through an angle of d theta, what's the arc length? It's actually r d theta. And so this side here is r d theta. So you make a cube here. Now, is this a perfect cube? No, of course not. If it was a perfect cube, then it would have straight sides. And these are curved. And because they're curved, the outer side is a little bit longer than the inner side. So this picture actually shows the inner side. I'll zoom in for you. It shows the inner side as r d theta, and the outer side is r plus dr d theta. Right? That's very technically correct. Now, what's not very technically correct is then the next step is they say, well, so this is just going to be, for the base, I'll take the area of a trapezoid. That is, r d theta on this side and r plus dr theta on the other side. That's saying, in essence, that these are straight lines. So they still approximated, but they've approximated a little bit less. So that they have the area is 1/2 bottom plus top times the thickness. When you do this, you're going to have 1/2 combining terms. I have a r d theta and another r d theta, 2r d theta plus dr d theta, and then the dr at the end. Now's where you wonder why they spent the time. How big is dr d theta compared to r d theta? R might be a centimeter. Dr is infinitesimal. How would you compare the two sizes? Centimeter to 1/infinity. How do they compare? This one here is negligible. We can say this one here is approximately 0 because it's so small compared to the other one. And then when you do that, this just becomes area is equal to 1/2 times 2 turns out to be 1. And so it's r d theta dr. If they had made the assumption that this was a cube, they would have said the area of the base was r d theta dr. So in the end, despite their technicality, they still have the same result. The base is r dr d theta, the height is dz, and so you end up with dv. This was technically a dA. They should have put a d there. dv is equal to r d theta dr dz. So that's the dv when you're using cylindrical coordinates. So now if I want to find the moment of inertia for this disk, I would say, well, moment of inertia about what axis? Let's start by doing the only axis I'm going to do. Let's do it about the z-axis, the symmetry axis. If I do it about the symmetry axis, I will have I technically have 3 integrals. Right? I'm doing this the long way instead of shortening it. I have 3 integrals, and I'm going to have r perpendicular. If you look at my disk, what is the r perpendicular to the z-axis? It's just R. So that's reason number one why cylindrical coordinates is easy for something that has cylindrical symmetry. Because the R perpendicular is just R if you're going about the symmetry axis. So I'm going to have just R squared for my R perpendicular squared. And then for my dm, I will have my density. Let's assume uniform density. Is that fine? Okay. So I'll just have my density times dv. And the dv is this thing here. R d theta dr dz. So now I break this up. Integral from, well, actually, I won't put the limits yet. I'll have you tell me. I'll put theta for the first one. Remember, I like to put my variable with the integral sign so I know which thing is being integrated. R squared times R is R cubed. And now I have to look at my limits. So what are the limits going to be for my angle? 0 to 2 pi, because I'm doing a complete circle. What are the limits for dz here? Okay, I'm just going to go 0 to, and I'm going to call it h, whatever the height is for this disk. I don't know what it is. And then for r, what's my limits for r? 0 to, and I'll put capital R. I'll say the full radius is R, a capital R. And so now, oh, and I forgot my rho. There's rho. Do these integrals. That gives me 2 pi. This gives me h. This gives me r to the 4th over 4. And then I have the rho. So there I've done all of my calculation, but we usually like to put this in terms of the mass, especially because right now I have 2 pi h, and I didn't even define what h is. H is the thickness of this disk. Well, what's the volume of the cylinder? It's what? It's the area of the circle, pi r squared, multiplied by the height, h. To be consistent, capital R. So since density is, if it's uniform, density is just mass over volume, then that's mass over pi r squared h. So I'll substitute this in. Notice my pi's cancel. Actually, change color. The pi's cancel. The h's cancel. And with my r's, I will have 2 r's cancel. And so I have I for the disk is equal to, everybody knows, 2 divided by 4 is 1/2. Canceling 2 of my r's. R squared m. Now here I calculated it very explicitly, not even taking into account the uniformity except for in the fact that my density was constant. And we got the same answer. Now for my last trick, trust me, 20 minutes is going to be making it tight for the last trick. Let's do the moment of inertia for a sphere. Now I will start by saying it's a uniform sphere. We have lots of uniform spheres. Some bowling balls are uniform spheres. Some are not. They make some bowling balls that are very intentionally not uniform spheres. They have weights in there to make it so you can, alter your shot, your curve. How do I know this? When I was at PHYS, I had a student who decided he wanted to be a really good bowler. So he had 2 balls, one for one type of thing and one for another, I didn't pay much attention, but the difference in the balls was their moments of inertia. One of them had a uniform distribution and one didn't. Okay, so getting back to this. If we're going to find the moment of inertia for a sphere, it will be most convenient to use spherical coordinates. So spherical coordinates are shown here. You have the angle, now its phi is filling the exact same position as the angle we had for cylindrical. So the phi goes from 0 to 2 pi going around a complete circle. So phi goes from 0 to 2 pi. Theta is an altitude angle that just goes from 0 to pi. And as I said a week ago, the reason that theta only goes from 0 to pi is if you went around for the second half of the circle, then you'd be going around the full circle horizontally and the full circle vertically. You'd be covering the whole circle or the whole thing twice. And so that's why that one only goes from 0 to pi. And then, of course, you have r that now, instead of being in the xy plane, is just going from the center out to your point of interest. So it's the distance from the center of the sphere. So r, of course, goes from 0 to capital R. So now I've already defined my limits for a typical problem based on what they mean. I need to know r perpendicular and dm. Those are the two things I need, plus my limits, to find the moment of inertia. So what would r perpendicular be? Let's say I'm going to rotate a sphere, uniform solid sphere, through its center about the z-axis. So r perpendicular is the perpendicular distance from that z-axis. What's that going to be? I'll start with a very leading question. R is not parallel to the z-axis, and it's not perpendicular to the z-axis. So what angle does R make with the z-axis? Theta. So if I wanted to find, for instance, the amount of r that's parallel to the z-axis, what would I do? Well, for parallel, I would use cosine. And since I'm looking for r perpendicular here, for r perpendicular, I'm going to use r sine theta. If you just look at this picture, well, I will flatten out the picture. Here's my z-axis. Here is r. Here's theta. I want that opposite side. And so this side here is going to be r sine theta. Because opposite side, sine over hypotenuse is, or opposite over hypotenuse is sine theta. And so my r perpendicular is r sine theta. dm, three-dimensional, let's just go with the basics. It's always safe to say rho dv. And so then I can put those in my integral. My integral, triple integral. And then I have r perpendicular squared. So my r perpendicular is r sine theta, quantity squared. And then I have my dm, which is rho dv. What is dv? It's written right here. We went through this last class period. dv is the r squared sine theta d theta d phi dr. So now with this long integral, it's completely separable. You might remember I wrote out, I don't remember if it was an integral for this or something else, but doing it in Cartesian coordinates and it was non-separable. You had to have limits that were based on another variable. Well, this is completely separable. I can break it up into my integral and I'll put d theta here. I have thetas. I have a sine squared theta and another sine theta, so sine cubed theta. And then for phi, there's no other phi's here. And finally for r, I have r squared times r squared is r to the fourth dr. For the limits, I wrote the limits right here. So phi goes from 0 to 2 pi, theta from 0 to pi, and r from 0 to capital R. Who can tell me the value of that integral? Oh, and I forgot to write rho. There's my rho. What's that integral? R to the fifth over 5. What's this integral? Two pi. What's this integral? Not so easy, right? There are two ways you could solve this. Way number one, what are you doing? Integral tables. That's what I was hoping you were doing. Way number one is look it up in the integral table. Way number two, well, yeah, you could do, I think you said integration by parts. You could do integration by parts. A trigonometric identity is the typical way you do this. You say sine cubed theta is equal to, obviously, sine squared theta times sine theta. But sine squared theta is equal to 1 minus cosine squared theta. And then you say, let u equal cosine theta. So du is equal to cosine theta minus sine. And then you have sine cubed theta is equal to 1 minus u squared times minus, well, sine squared theta d theta cubed theta is equal to that. And that's very easy to integrate. Okay, but you got out the integral table, so... Oh, come on. Gonna make me do this?
I assumed you were just doing that. So.
Okay, so if I'm gonna continue on, well, we're just about to the end point of the integral. If I integrate this, integral from 0 to, what was my limit? 0 to pi. Then this is going to be integral from, I'm just going to go sine of 0, or not sine of 0, cosine of 0, to cosine of pi. Does that strike you as fair? Since I made the substitution that u is cosine theta? What is cosine of 0? What's cosine of pi? Minus 1. So I'm integrating now from 1 to minus 1. Do the integral, and I'm going to have this minus sign I'll put out front. U minus u cubed over 3. From 1 to minus 1. Put in your limits. Okay, minus 1 cubed is still minus 1. So that's why this is a plus sign here. And then I have minus, and then this one here is going to be, I believe I put all my numbers in right. So that is minus 1 is minus 2. Plus a third means minus 1 1/3, my sign, plus 1/3, or 4/3. equals 4 over 3. So I can come up here and put in 4 over 3 there. So 4 times 2 is 8. 3 times 5 is 15. That looks big and ugly, right? But remember, by definition, since it's uniform, the mass over volume is equal to rho, which is equal to mass over 4/3 pi radius cubed. So if I make that substitution, now I have 8 divided by 4 is a 2 on top, and 15 divided by 3 is a 5 on bottom. Everybody convinced 8/15 divided by 4/3 is 2/5. And then the pi's cancel. 3 of the r's cancel. And there we go. Got the moment of inertia of a sphere rotating about its center. That was a uniform sphere. Is the Earth a uniform sphere?
Yeah.
Jaron? For calculational purposes, Jaron says yes. I put in a blank page thinking I would use it, and then I squished everything on that page. Here is a graph showing the density of the Earth as a function of depth. You have the crust of the Earth is that region. The crust varies, over here it shows you, from 30 to 65 kilometers, it says. The crust, actually, the oceanic crust, gets down to about 7 kilometers at its very thinnest. So we have that crust, which is non-uniform in shape, because the thickness varies. Once we get below that, the Earth is very uniform in its spherical shape, but the density is not uniform. So you can see here some variations going on. Whoops, that's not a vertical line. Variations going on essentially for the first about 700 meters going down to this point here. Now, just a little bit of geology, because you probably don't know all of these things. If you go through the layers of the Earth, you of course have at the top the crust. At the bottom of the crust, you have the Mohorovicic discontinuity. It's where you essentially change from the kind of stuff the crust is made out of to the kind of stuff the mantle is made out of. They're very similar in nature, but the mantle is, you see over there on the left, mantle plastic. What does plastic mean? Besides a type of container. Not changing, but it means that it can be deformed. So that mantle is deformable. It is basically the same type of stuff that we have in the crust, but it's compressed at a high enough temperature that it just kind of oozes. Like very thick molasses. And so once you get to this point here, okay, so at the Moho, that's what because nobody likes to say Mohorovicic. At the Moho, you have it changing to the mantle, which is much more consistent. And then you get down here to 700 meters, and it doesn't have it named, which is surprising. This is called the asthenosphere. The asthenosphere is that separator between the upper mantle and the lower mantle. And that's a region where the temperature and pressure are just right that you have the ability to slide. So the upper mantle and the crust slide on top of that asthenosphere. the stuff below that stays very, very constant in position. So if we have tectonic action, that is, if we have pieces of the surface of the earth floating around, those pieces have to be everything that's up above here, above the asthenosphere. So this stuff up here put together is called the lithosphere. I know, this isn't a geology class. I don't know why I feel compelled to make sure you understand the earth. But I do, because it's physics and the earth is part of what we study. So the lithosphere is the part that is what actually moves. The tectonic plates are made of the lithosphere. So it's the upper mantle and the crust that makes up the lithosphere. Then down here, it's very uniform in the mantle, just getting hotter and hotter until you get to the molten core. So here's the molten core, and then you finally get to the solid core. I can't stop. We have some very special volcanoes on Earth. One of them is the Hawaiian island chain. One of them is, I don't know what directions what. I've never figured it out since I've come to Nebraska. But if you were to go to Yellowstone Park, it's another one. Both of those are volcanoes that come from deep in the earth. They are not the normal kind of volcano we think about, which come from grinding of rock. They are hot spots where you have stuff in the mantle that is coming up and making it a volcano. Now, those volcanoes tend to ooze more than anything else. So Hawaiian Islands, you just have the lava oozes out and flows. Makes what we call shield volcanoes, so the Hawaiian Islands are shield volcanoes. All of the Hawaiian Islands are the same volcano. But the crust, well, the whole lithosphere, has moved over it so that it punches up here and makes a volcano, makes an island, and then it moves along, punches up again here, punches up again here. And that's why you have a chain. Because as the crust and the upper mantle have moved over that hot spot, it punches through in different locations. Question?
Why isn't it like a single mountain ridge? Lithosphere is moving continually, right?
The lithosphere is moving continually, and you are actually building up pressure underneath so that you can actually have two places where it pushes up through at the same time. So you can have two volcanoes going at the same time from that same hot spot at different locations. So it's kind of, it found a soft spot that it could get through here. And of course, the one in Wyoming, I believe, is also coming from the lower mantle up through the mantle. And when that one erupts, it tends to be pyroclastic and it's explosive. So that we have things like the ash falls, if you've ever been there, where you just have lots of ash from the eruption. Anyone here been to the ash falls? One. Me too. You have a lot of ash that buried most of Nebraska. And over there you have, many meters of ash, and so it buried lots of things, and you can go dig out. Well, you can't, but they have dug out and found the animals that were living in Nebraska at the time of that eruption. And you can look, they have maps there showing you the different locations where the Yellowstone volcano has erupted because of, once again, tectonic motion. And now I'm out of time. Well, what would we do with this if I had not run out of time talking about geology? We would try to model the density of the Earth with functions. You might say, well, let's make this a straight line, a discontinuity, and a straight line, and get a much better measurement for the moment of inertia than you would if you just said that it's uniform with one density throughout. That was my point with this. The other point was I thought I would have time to actually go through the calculation for the acceleration of gravity as you go deeper into the Earth, but we won't. So, have yourselves a swell morning. I'll see you again at lab at 2.